Log on, tune in, find out. Another good idea from Cambridge.
And local lad, Tom Sanders, who's somewhere between a theorem and a conjecture.
Yeah, thanks. So I'll be talking about Freiman's theorem. It should be a fairly relaxed sort of introductory talk. I used to give an introductory talk on the Roth-Mechelin theorem, but then Bateman and Katz sort of solved the problem in the sense that I like to state it. So this is my new sort of introductory level talk. Okay, so the setting is G is an abelian group. And just so we're clear, the subsets of G, I define the sum set in the usual way. Be what you think it is. Okay? And these sets will be finite. Okay? I'm thinking of G, if you like, as being discrete. So the starting point, or a nice starting point here, is the idea of what a coset is. Okay? So you could say that A in G is a coset, right? And I want to write this in a certain way, say, of a subgroup. If, then I suppose you have that A is non-empty, and then that its sum set is the same size as the original set, right? So it's the normal definition of a coset. Not the normal definition, that is a definition of the normal notion of a coset. And so I want to think about relaxing that. So it's not interesting to relax the first condition. So I want to concentrate on the second condition. So and I want to consider sets A and G. As I say, there's the finite sets with some set, so A plus A, size at most k times the size of A. And so you think here of, say, the size of A as tending to infinity and k being fixed, or k tending to infinity very slowly with the size of A. If you like. Okay. So obviously cosets satisfy this. And in the first instance, as you let k be a little bit larger than 1, this sort of, in some sense, remains more or less the only example. So this is a rather cute result, been known for a long time, I think, due to Freiman. Which is that if A plus A has size at most 1.5 times the size of A, then A is contained in a coset H of size at most the size of A plus A. Okay. The proof of this is very easy, and it involves one important piece of notation, so I just want to sort of sketch it and in particular introduce the notation. So I want to talk about convolution, right? And I want to define this using summation. So I'm thinking I have two functions, f and g, and say L1 of g. We think of them as having finite support, if you like. And then I define f involved with g pointwise as, say, the sum over y plus z equals x of f of y g of z. You think of it as an averaging thing, right? This is somehow f averaged over g. And then the basic idea is just to show that A minus A is in fact a genuine subgroup, okay? Okay. And you do that by looking at 1A convolved with 1A. So I said this is an average here, right? So you expect 1A convolved with 1A to be quite smooth, right? And it is. But this small doubling condition will ensure that, in fact, on the set A minus A, 1A convolved with 1A is necessarily very large, so you have a sort of jump. Okay? So formally, what you might do is, well, suppose that x and y are in A, then 1A convolved with 1A of x minus y. So if you just decode that here, it's possibly up to signs equal to this. Okay, and then this is just an inclusion-exclusion situation. Well, it is, yes, okay. Minus mod A plus A. So that's at least 2 minus k times the size of A. So if you think about it, this thing here is counting. It's the number of, this counts the number of representations of the argument as a, I should have a minus there, sorry, as a difference of elements in A, okay? That's just what this counts. And so what you have then, for any, this tells you that any given element in this difference set, okay, and it certainly has that form, can be represented as a difference in strictly more than A over 2 ways. If this is 1.5 here, right? But that means that 2 of those representations, so let's write them down. Suppose that U and V are in A minus A, then there exists at least A over 2 representations of U as A minus B. And
this little point is 2 minus k, yes?
here?
Yeah, it's minus.
Yes, that's a minus, exactly. It's the same minus as that. With all these guys in A. Right? But then, again, by the pigeonhole principle, that means there are 2 representations. There's at least one representation, well, a representation of U and one of V, where these 2 are the same. So when you add U and V, you get that it is in, say, A minus A. Okay? Then A minus A is also symmetric, trivially, and non-empty, so it forms a subgroup. So it's just a sketch, and the important thing I wanted to highlight is this guy here, because I want to use that in a moment. Now, okay, so you could imagine that that phenomenon persists, but it doesn't. Once k gets to 2, a new phenomenon occurs, okay? So once k arrives at 2, we get arithmetic progressions. Right? if P is an arithmetic progression, you add it to itself, then you get a set that's twice the size of the original set, right? P is an AP. Then P plus P, most, say, times the size of P. Okay. So we've got these subgroups, or these cosets here, okay, and arithmetic progressions here. And it's not too hard to see, actually, that you can combine those, okay? And so that leads one to sort of fairly natural combination of these structures. So we'll say, well, I suppose let's do a generalized, well, a coset progression. Of dimension D. Is a set of the form P1 plus dot 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 plus PD plus H M, where the PI's are arithmetic progressions and H is a subgroup of G. Okay. Put some more white. It's called a coset progression. So the progressions, these arithmetic progressions here, can be a totally different common difference. And in general, they might well be. A nice example to think of is if G is, say, Z to the D-dimensional lattice, and these progressions are, say, intervals in the D different directions. And you have, say, no subgroup. So this would then be like a cube, okay? And that's sort of how you want to think of these things, as convex bodies plus subgroups. Okay? Why have I defined this guy? Well, I've of course defined this guy because he has small doubling. And so does any large subset. So, what do I mean? Well, now suppose that suppose M is a coset progression of dimension D. And A in M is a large part of M, okay? Well, let's actually, I'll write it like this, sort of to help with things a little bit later. Then it's easy to check that A plus A has size at most, whatever, e to the D plus H. In fact, a much better bound than this, but or a slightly better bound than this, but this is sort of emphasizing what I care about. So again, just think, you have a d-dimensional, say, convex body, and r to the d, say you add it to itself, it gets about 2 to the d times bigger, right? So these guys, and large subsets of these guys, form a large family of things with small doubling, okay? And the reason I've gone through all this process of telling you about all these examples is because this is in fact everything, okay? And so this is within additive combinatorics, the well-known, but otherwise simply Freiman's theorem. That's proved by Freiman rather than Freiman's theorem. So this is Freiman's theorem. And in the generality and form I'm about to state it, it's due to Green and Ruzsa. And it just says what you think it says. So it says, suppose A and G, leading groups, have doubling k, then there's a coset progression. M containing A such that, say, dim M is at most some function only dependent on k, and the size of M is at most some other function only dependent on k times the size of A, so it's linear in the size of A, okay? This is some function h and some function b of k. So this is a qualitative converse to what we just did, right? I've shown you that every large... I rub out exactly what I'd written, didn't I? Okay. Every large subset of a low-dimensional coset progression has small doubling, and this says that every set with small doubling is a large subset of a low-dimensional coset progression. Okay? Maybe I...
Some of your examples in the like z to the d, and you take intervals in every.
Yeah, if you like.
Then
Yeah.
what will be the k?
K will be about 2 to the d. Just think sort of in R, yeah, it looks roughly, I'm thinking always as the size of the set is going to infinity, so it then becomes roughly like R to the d. Because we're only adding things with these problems, only adding things together a small number of times, you can simulate z to the d in z just by sort of imagining all the numbers in a sort of very large base, a very large high base. So you can map here. Okay. So then you sort of want to know, I want to mention a little bit about bounds. So Freiman-Ruzsa showed you can do some fiddling to modify d of k. D of k is the least interesting of the two. You want to control h. That's somehow the hardest one to control. Okay. So they showed that basically k to the 4 works, and then showed that k to the 3. Schoen and Colina showed that k to the 3 works. And it turns out that, well, k works. The little o there, it's called the k to the little o of 1 is in fact a log k, sort of bigger of 1. But actually, so this is essentially best possible, right? And so if you can simulate this in other abelian groups, but what you want to think of is, suppose you have a subgroup of f2 to the n, and so let A be a union of k independent cosets in the quotient space or group or whatever. This is a vector space. Okay? And that has doubling about k. But if you had to contain it in a subgroup, it's certainly contained in the group generated by A, the smaller subgroup that contains A, certainly. What is it? Group generated by A. So that would have to have these k independent points. And you would find that this, although D is very small because coset progressions are not interesting in f2 to the n, your h still has to be linear in k. Okay? So in some sense this is best possible. But that actually reflects it is a poor choice of theorem. Because, well, first of all, because I end up going from something with about, if I was in Z, I'd end up going from something with doubling about K, I'd produce something at the other end, which I wouldn't know had doubling anything like K. It might have doubling sort of more like exponential in K. So that's not illustrated by this example, but it's illustrated by, say, a variant of this example in Z. So somehow I would have an exponential loss in repeatedly applying this. Not that you ever would repeatedly apply this, but you know, this sort of reflects a failure of the result. And it's somehow also clear, right, because you're trying to sort of seek out some kind of structure here. And well, this guy is really very structured, right?
What is B?
So B, oh yes, H. So I'm just thinking, take a subspace, and that's really the bit we want to find, right? If I take k independent copies of the subspace, I want to focus on one of those cosets, right? That's the bit I want to see here in my work. So that motivates a better way, or a better theorem framework. So this doesn't really have a name. This is the thing that's somewhere between, because it doesn't unfortunately prove the conjecture of the title, but because it's a theorem rather than conjecture. But it's better than this. So it's not due to me either. Let me just say it. So again, suppose that A and G has this doubling condition. Okay. So then I want to formulate something that's not containing, but correlating with, right? So then there exists a, let's say, I'm going to use D and H again, because I'm never going to talk about that again. There's a D of k-dimensional coset progression M, such that this is a large part, let's say, of M, and M is itself large. So I'll say a moment. Okay. So what is this? It's low-dimensional coset progression. A is dense on M, in the sense that it contains a proportion 1 over k of M. And M is not too tiny, right? Without this condition, just take M to be a point, right? And I can beat that bound and that bound very well. But so M is large, has these properties. Why is this good? So you want M to be large. This is a good situation, right? Because if k is fixed, you're sort of in a dense regime, right? You have an object M which behaves very much like a group in the sense you can do Fourier analysis, you can do all sorts of stuff you want to do normally. And you would be analysing this set A relative to M in a regime when it's dense, which is when the Fourier transform is strong, right? I mean, if you're not dense, if you're sparse, then the Fourier transform is very weak. Okay. So here I guess say Green and Ruzsa, and then Schoen, it's sort of the same thing, shows again, you can take more or less the bounds of 4. And we go to the 4. Schoen had much better bounds in the case of specific groups when G is Z or G is F2 to the n. In both those cases, and the cases that sort of followed for them, he had much better bounds. And those are the important cases, actually, in many senses. But in this case, it turns out that you can, in fact, show a sort of polylogarithmic bound. And this example doesn't cause you the problems here, but you can nevertheless show, just by supposing that A was, say, a d-dimensional arithmetic coset progression, just a fixed one, genuinely d-dimensional, then you can show that this must be at least log k. Okay. A fairly simple example shows say d of k and h of k. This is not quite, let's just say h of k. Be at least log k. So in G equals F2 to the n. So here I was a bit loath to write the n because somehow this is not a relevant n. This just adds a variable you should never be talking about. Yeah. Somehow A has some size tending to infinity, but it's still potentially very sparse in F2 to the n. G equals F2 to the n. This is the conjecture of the title of my book, the Polynomial Freiman-Ruzsa conjecture.
Right, sorry, can I change your battery?
Yeah. Speak a bit faster.
Tom, you didn't tell us whose theorem it is.
Yeah, okay. So the polynomial Freiman-Ruzsa conjecture then is that you can take this h of k of big O of log k. Okay. So this would be very nice. I want to advertise this here.
This is just a model case for the.
Yes, but there's a slight. In general, there's a slight problem with what sort of convex body you choose. Imagine. So I gave you this example of, say, the cube in z to the d. Okay, but suppose my original set A had been, say, the sphere, the Euclidean sphere in z to the d, the sort of lattice points inside the sphere in z to the d. Okay, thinking of the radius of the sphere as tending to infinity. Then the way I've defined a coset progression, I'd have to contain that in a cube. So my h here would have to be wouldn't quite be log k, it'd be sort of log k log k. Just for containment of convex bodies, you know, I have a sphere and I need to contain it in I've fixed my convex. So there's probably a correct conjecture somehow where the right definition of h of k, like h of h, doesn't it? H of k is also big O of log k in general, but this is, I I think this is definitely believed. Okay. Or at least, if you can find a problem with this, if you find a counterexample of this, somehow this probably is already interesting, right? But there aren't sort of, we don't know kind of trivial reasons why this wouldn't be quite the right thing. Okay.
Oh, but this theorem is still an exponential improvement on what we knew, I don't know, a couple of years ago. So are you telling us something about it? The theorem?
Yeah, yes, I will. Yeah, I just get it. Yeah, yeah. Yes, because fortunately it's actually very simple. What's that? Did I just? Let me say in words before I talk about that why it might be useful. It's not sort of clear, right, that this doubling condition, this having small doubling, is necessarily so much easier to satisfy than being this quite rigid coset progression type structure, right? But so it turns out there's this result, Balog-Semredi-Gowers theorem, that lets you pass from having many additive quadruples, that's many solutions to this, to a large subset that has small small doubling. And you could then apply a result like, say, this if this were true, or these results otherwise, to show then that something that you can check very inexpensively, right, that you have a large number of these, you can just sort of randomly sample from your set, for example. That's an easy thing to check, and it comes up in many, it's a very easy condition to satisfy. Okay, it's a robust condition to satisfy. You can use you have an easy condition to satisfy to spit out a quite structured object. Okay, so you sort of are somehow genuinely making progress. It's a genuinely useful thing. Okay, so let me talk about how you go about proving this in, and I will now focus on this case, f2 to the n. Okay, so there are two ideas. So the first one is I suppose it's an observation of Lopez and Ross. And this is just that this inner product here now let me tell you what all the parts are. So A and G, say G is f2 to the n, has density alpha, and well, mu minus A is the uniform probability measure on A. Okay, so this is and this is just whatever sensible inner product you want to take. Sorry?
On minus A.
On my, yes, sorry. Yeah. Yeah, you're right. But yeah, okay. So you can just check this identity, right, by moving convolution to the right-hand side. Okay? So convolution to the right-hand side, this becomes 1a convolved with mu a, and that certainly has support on a plus a. Okay? Just take the adjoint of that operator to that side. And so then it's an inner product of something with its support, which is just the integral of that thing, right? Which is just that on the right-hand side. Okay? And the second result I'm going to want to use is a lovely lemma. This really advertised.
To get the support of a plus a rather than of a.
The support of a plus a rather than of. The support of. So what you have is that is equal to convolved with mu a, right? And so this is supported on a plus a. Or you're saying something different? No. So this is just then the integral 1a convolved with mu a, and then this is just the integral 1a, which is the measure. Is that all right? And the other ingredient is the lemma of Crouten-Cisa, okay, on the LP invariance of convolutions. Okay, so how am I going to? I'll state that in a moment, and how I'm going to use it. Now, what do we get to? Oh yeah. So I want to make one simplification which is not, well, one further simplification which is not a dangerous one to make. What I should actually like to prove, we shall prove, well, I mean, really we shall sketch the proof of Bogoliubov's lemma. And so this is, suppose A and F2 to the n density alpha, then I'm going to write 2a minus 2a. I mean, it's obviously the same as 4a. Contains a subgroup of density. Well, let's say of codimension. Log the big O1 alpha inverse. Codimension is just the log of the log base 2 of the index. So this result actually follows very easily from this by a modeling argument, okay, due to Green and Ruzsa. That's not the, that is, this may seem slightly unbelievable, but that's not actually the new ingredient here, okay? Good. So what do we do? Well, so I said earlier, right, convolution is like averaging. And so this really is, the way I've normalized this is some function here, this 1 sub a plus a, and you just average it then over translates of a or minus a, okay? And so we expect that to have some kind of weak continuity properties, okay? And in particular, we expect it to say be invariant over some large set. Now, suppose we knew there was a large subgroup V such that this guy and I'll define these things in just a moment, was basically invariant in LP for all translations, all elements T and V. Does that, you see the bottom line there, okay? This is just translation by T, okay? So you just think of this, is translate this by T, and I'm saying, suppose you don't vary much in LP, as if you do that over some subspace V. Suppose we had that situation. Well, what am I thinking of here? I'm thinking of P as being large, okay? In particular, not 2. In fact, about log alpha inverse. Okay. Well, then it's fairly easy to conclude this conclude this proposition. Okay, because what will I do? Well, I can certainly average this over all elements T in this set V. So certainly then I get, by the triangle inequality, that 1A plus A convolved with mu minus A convolved with mu V minus 1A plus A convolved with mu minus A in LP most epsilon. But that means up in this little chappy up here, I get, by the triangle inequality, that this is equal to, well, at least alpha minus, well, what would I do? I'd apply Holder's inequality. So I get epsilon times 1A in LP prime. Right? So I just do an LP prime estimate up there. So P prime is the conjugate index of P. So then I say I put whatever. Say epsilon is 1 over 1,000. And P is, say, log alpha inverse. Okay. Then this is whatever. 0.99 alpha. But this is very good because F2 to the n is a commutative, well, it's a very commutative group, right? And so this means that convolution commutes. So I can take out an L infinity of this guy, an L1 of that guy, and it's at least 0.99 alpha. Okay. And this, if you unpack it, this here, the values of this is just the density of A plus A on, the value of this at x is the density of A plus A on x plus V. Okay? So this means there is some x such that A plus A contains 99% of x plus V. Okay? That's literally just unpacking that definition. So this is convolution here, dividing by the size of V. So when I cancel my alphas here, I get the convolution somewhere is at least 0.99. And this convolution is exactly A plus A intersect x plus V over mod V is at least 0.99. But that means then when I add A plus A to itself, I must contain the whole of V, right? By the pigeonhole principle. Okay. So this situation is very simple. It's a bit like Rudin's inequality or Bechter's inequality. It's a very simple situation, and this motivates then why I would want this LP invariant statement. Okay. And then fortunately, Croot and Cisask more or less proved such a result recently. Okay. So suppose F is in LP. Everything's finite, so it doesn't really matter. And A and G has doubling at most. Okay. Then there's some large set T. These will be sort of good translates, which are invariant. of size at least. And I'll tell you what this epsilon you can specify. Maybe I'll put that up here. Say in 0, 1, there's maybe some other trivialities you want to avoid, but exists a large set T such that f bang mu a translated by T minus f bang mu a in LP is at most epsilon times f in LP for all T in T. Okay, not good enough. It's not T is not a subspace yet. Okay, it's just a large set. Right? So I'm finding a large set over which this guy is approximately invariant. Okay. The great thing about this large set, well, let me just say, it's a lovely 1-2 page proof, this lemma in Ernie and Olof's paper. Thoroughly recommend reading it. The idea, it's a really, very natural idea. You just randomly sample from your set A. And so you approximate f convolved with mu a by some small number of translates of f. Okay? And then apply the triangle inequality. It's a very nice argument. I thoroughly recommend it. Okay, but so this doesn't necessarily look like we're really in a winning situation yet because T doesn't have this structure. But another aspect that they observed is, of course, you can sort of add structure to T, right? Because you've got the triangle inequality here. If I put a 2 there, I can put a 2 here, right? And more generally, a K and a K. Okay? And so, and this is going to cost, you know, for this to be small, eventually it's going to cost me up there in terms of K. But I can use that increase in K to introduce structure into this set T. Well, not into the set T, but, you know, structure into the set of things over which one is essentially invariant. Okay? And so that, let's see here. And that is basically the only other trick is you get, yes, okay, so you get here, and instead of V, instead of mu sub V, you have a situation where you have mu sub T convolved many times. Okay, so you have 1a plus a convolved with mu minus a convolved with mu sub T. That obviously means convolved with itself k times. Inner product 1a is at least, whatever, let's say 0.99 alpha. This then has a, do the obvious thing, right? Just whack out the Fourier expression for this guy. And then we're in really good shape, right? Because if I choose k large enough, then I only need to consider the characters where, say, mu sub t hat of gamma is at least a half. Okay? Because I'm boosted exponentially by this k. This k sort of kills off an error term exponentially. Okay? So I can, in fact, takes a little bit of, you know, if you're familiar with these things, it's very clear, and otherwise you just have to believe me. I can, in fact, define V to be the orthogonal complement of, well, let's say the large spectrum of this guy. And the codimension of this can be estimated very effectively using something called Chang's theorem. If you put those ingredients together, you'll find we proved the proposition. You find you can prove that proposition up there. Okay, so it's the Lopez-Ross observation, this translation invariance, and then it's a fairly, I mean, I'm not giving the details here, but it's actually not a, it's not a particularly tricky Fourier argument with Chang's theorem. Takes like page and a half, something like that in F2 to the n to do this argument. Sorry? In which font, right? Okay, of even a reasonable font. I think I'm possibly even write in 12 there, with a title. But I will end there.
So, more questions, Omar?
In the crude cisat lemma, if p equals 2, then I think T can actually be a subspace, right?
Absolutely, and more than. Sorry, you have a follow-up.
Is it possible that it could be a subspace for p equals 4? Or is that impossible? Do you know?
Presumably it is, in fact, in general, a subspace. And it would be nice to have, to have that additional strength. And if you had, you would improve you can get sort of, instead of you get log to the 4, okay, you could get down to log squared. There's an obstacle to getting better than log squared of a different character type. But yes, you get down to 4. The other thing to say is the difference between this and with p equals 2, you can also make a more universal statement. You can move your set T is dependent on A and epsilon, but not on F. Okay, whereas here the set T, one of the reasons their argument is sort of nice in the way it is, but it necessarily depends on F. So there's a sort of universality that you can, an additional universality in p equals 2 that I would love to have a use for. I unfortunately don't. But yeah, I guess it's I have no idea that it's not a subspace.
Any further questions?